This video explains how the temperature and the composition of the lipid bilayer can alter how fluid or stable the membrane is. The lipid bilayer is kind of like plastic or leather. When it's cold, it becomes very stable, less fluid. When the membrane is warm, it becomes very fluid, less stable. Think about the leather seats in your car when you sit down and it's hot outside. Your seats are soft and squishy, but when it's cold outside, you sit down and the leather is hard, stiff. Okay, when it comes to the length of the fatty acid tails, if these fatty acid tails are long, they're going to hold hands and they're going to prevent the membrane from wiggling a lot. If the fatty acid tails are short, the membrane will increase in fluidity because they're not going to hold on to each other, they're not packed, and they're going to be able to wiggle independently of these. So because these are not touching, these phospholipids can wiggle and these don't have to. The membrane will be very stable with short phospholipid tails. With long phospholipid tails, they hold onto each other. So in order for this phospholipid to move, its partner over here on this side of the membrane also has to move. So long fatty acid tails decrease fluidity. Short fatty acid tails increase fluidity. When it comes to the unsaturated kinky fatty acid tails, the unsaturated kinky fatty acid tails don't pack very nicely. They don't pack tightly. So the short, unsaturated kinky ones increase fluidity. These straight, saturated fatty acid tails pack very nicely and tightly together. Because they stack so nicely, they decrease fluidity of the membrane. The membrane would be more stable. Now, this yellow cholesterol, if we increase cholesterol, we add cholesterol, you decrease fluidity. Add cholesterol makes the membrane more stable. Cholesterol, think of it like hard, solid butter. Okay? It's going to make the membrane stable. If you remove the cholesterol, the membrane becomes more fluid. So we have the organisms here in this example at various temperatures. We'll start with the human being. Humans live between 15 degrees Celsius and 30 degrees Celsius. You can see we have a medium number of short saturated fatty acid tails and more unsaturated fatty acid tails. We have a medium number of short tails to long tails, and we have a medium number of cholesterol. You can see that if we increase the cholesterol, we make the membrane more stable, less fluid, and that's not good because stuff can't get in and out. If we completely leave out the cholesterol, the membrane becomes too fluid and it falls apart. Okay? Short fatty acid tails. If we add the short fatty acid tails, notice we increase the fluidity. Remember, the phospholipids are not packed in tight. The phospholipids can move all over the place and the membrane's quite fluid. But if we make long fatty acid tails, the tails are holding hands, the membrane is very stable, cannot move and stuff cannot get in and out. With the straight, saturated fatty acid tails, if we add them, remember everything's packed real tight. So our membrane is not very fluid. Conversely, if we add unsaturated fatty acid tails, everything's all kinky and loosey-goosey and nothing can pack tight, and so the membrane's very fluid. So we need just the right amount for human beings to live. So let's try this bear who lives at a very cold temperature. Because the bear is living at a cold temperature, its membrane is not very fluid. The bear needs to adjust the membrane to increase fluidity. So to increase fluidity, to make it more wiggly, we're going to take out the cholesterol. Okay? You'll notice that as I move out the cholesterol, this little dot moves toward the viable green area. Okay? We're going to add some short fatty acid tails. We're going to have more short fatty acid tails than long fatty acid tails. And we're going to have some more unsaturated, oops, there we go. There we go. So this grizzly bear, in order to live in the very cold temperatures, has no cholesterol in his membrane, has a whole lot of short fatty acid tails, and has a whole lot of unsaturated fatty acid tails. Look at all these kinky short tails. All right, let's move on to the lobster. The lobster lives in a little warmer temperature, so he's a little closer to viable. So again, let's start with the cholesterol. And taking out the cholesterol is going to move it to a little more viable. Let's see, it's too stiff, so we need to add some short fatty acid tails. And it's still too stiff, so let's add some more unsaturated. So we got some kinky, but we have some straight. We've got some short, but we have some long, and we have a little bit of cholesterol in our lobster cell membrane, and it is viable. We've already done the humans. Now, this tropical fish lives in a warm environment. The membrane is too fluid naturally. So we have to decrease fluidity. To do that, we're going to have to add some bacon grease. And then we want it to be more fluid. Less fluid, I'm sorry. We want it to be less fluid, more stable. So we're going to add some long fatty acid tails, and we're going to add some saturated fats, and that's too much. So let me take out, there we go. So more cholesterol increased the stability, decreased the fluidity. More long tails decrease the fluidity. More saturated fatty acid tails decrease the fluidity. Last one, these archaeobacteria that live in the geothermal vents don't even have cholesterol as an option. Because it's so hot, 40 degrees Celsius and hotter, the membrane is very fluid. So we've got to do something to make this membrane stable. To get the membrane stable, we need those long fatty acid tails to hold hands. And we need saturated fatty acid tails to pack in nice and tight. I hope this was helpful. Thank you for watching.